All right, everyone. Thank you all for coming tonight on this. What day is it? On this Thursday, I think. Yes, it's Thursday. Thank you all for coming to this new edition of the Berlin Unstructured Data Meetup. If you need the Wi-Fi password, I put it on the slide because I had no network when I arrived. So take a picture if you want, and otherwise I'm going to start. So for the people that don't know who I am, I'm Stefan. I'm your host tonight. I'm also the first speaker, so you'll see me for a bit. And yes, I'm a developer advocate at Zilliz and Milvus. So if you have some questions related to AI in general, or vector database or anything, feel free to reach me out on LinkedIn or on Twitter or per email as well if you really want to. And I usually am available about everywhere. So just quick reminder, just be respectful and kind. Yeah, all ideas are welcome. So if you want to share something, feel free to do so. And if you see something that is inappropriate, feel free to let me know or to let people from HelloFresh know as well. And then we will help. Just in case, if you need getting started with vector database, you can scan those two. So we have Milvus, which is open source, where you have to manage it yourself. It's self-managed. And then we have Zilliz Cloud, which is our cloud offering. And usually people ask us how we make money. That's through Zilliz Cloud. So yes, if you want, you can check it out directly. And also we're hiring. We are hiring in the US, in Japan, in London. So if you want to join as a developer advocate, software engineer, solution architect, I think we're also hiring in Japan. Feel free to let me know or then scan this QR code directly. You can also join our Discord if you have any questions. Would be helpful. Be happy to help you, like myself or the engineers or the developer advocates that we have. And if you want to become a speaker as well, I organize those monthly. So you can either come to me at the end, tell me on LinkedIn later, or then you can just scan this QR code directly and then you fill out the form and then maybe you'll become a speaker at the next one. If you build something cool with Milvus or Zilliz, let me know about it because first I have some swag with me. So then you can get like a jumper or you can get some t-shirts. So yes, feel free to let me know and tell a story and then maybe I have a jumper for you. Also, usually we have a price. So if you scan this QR code, I have like a lot of t-shirts to win. I mean, lots. I have like 10 because it's very warm today, so I didn't want to carry like 200. So I have like about 10 t-shirts today, like some socks and stuff. So scan this QR code then, and then you might have a chance to win a prize at the end. I'm just gonna let it on because I see some people taking pictures. And then once we're good, be all right. Yes, feel free to share pictures on socials. It really helps me. It really helps us to raise awareness about the meetup so we can do those more often. And then we can also have more venues, reach out and different things. It's really, really helpful. Tonight we have 3 talks. So myself, I'm going to talk about multi-agents and I'm going to use Mistral AI tonight. You'll see me using Mistral Nemo and Mistral Large and I'll talk more about that. We'll also have a talk about the journey of large language models at GetYourGuide. And then we'll also have a talk that is going to be from CLIP to JinaCLIP. So general text image representation learning for search and multimodal RAG from JinaAI. So yes, we'll have 3 talks tonight. And again, if you want to speak at the next one or at another one in the future, feel free to let me know. Join us at the next meetup, which should be on October 2nd. It will be at Google again. And I'm going to actually ask our host to come on stage. HelloFresh is very kind to give us the venue. So they are going to talk quickly about HelloFresh. Everything. Thank you.
All right, welcome everyone. Before I actually start giving an intro about HelloFresh, I just want to ask how many of you actually tried some of the delicious bugs from HelloFresh before? Raise your hand. We got some folks. Okay, so some folks here, so I think I can make the intro part pretty quick then. So a little bit about HelloFresh. Our mission basically is to change the way that people eat forever. And our vision is basically to become the world's leading fully integrated food solution group. So you tried our meal kit, but we have a bunch of other brands around ready meals and even pet food that are coming soon in Germany, but mainly prominent in the US. So the direction that we're going to take in, we're going to be a fully integrated food solution that you can get basically any type of meal from your breakfast, even pet food, or if you love to get meats, you can get subscription for meat even. Or if you're a picky eater, you can get stuff which is more for picky eaters. And the way that it works is basically as simple as a couple of steps. So we create a unique recipe for you, which is tailored to your food experience. Of course, we source our ingredient from everything fresh and mainly locally sourced. And then in our platform, we recommend what you choose and confirm what you want to eat in the end. And you get your delivery received by your courier, and you start cooking. So that's the delicious part, that basically you can use the recipe that we provide and cook your own meal, and you can enjoy the taste of the meal. So here is a couple of simple steps, basically how you can taste our product. And since this meetup is actually about the data, so I put some data around where do we stand around the numbers as a business. So we are the first meal kit company in the world. And just to give, let's say, some sense of how big is like the number of boxes that we delivered, just in 2023, we delivered over 1 billion meal kits in the world, which is quite massive. And we operate in multiple markets as of now, 18 different countries, and we have more than 12,000 recipes in our database and more than 20K employees. So with that, I also wanted to share a little bit of, let's say, our hiring here. So if you like to be part of something delicious, if you love food, as we all do, sign up and check out our career page. So we have some opening roles mainly related to data, AI, and ML. Like we have a senior ML engineer open, staff product manager for recommendation and personalization, or principal PM for experimentation platform, and data engineers. So these are some example of the roles that we have, and I found to be relevant for today's event, but we got way more that you can find all of them in our career page, which is career.hellofresh.com. And that was it from my side. So welcome everyone. I hope you're going to enjoy the rest of the meetup.
Thank you very much. Oh, sorry, I was very long. For the people on the left, if you want, we have some seats there on the whole other side. Just letting you know. I have to share my screen again, and then I'll be back. I'm gonna share my window. Hey. All right. So yes, I mentioned I would talk about multi-agent systems, and tonight I'm going to use Mistral AI. I'm going to use Milvus, and then I'm going to use llama-index with the new released llama-agents, which was released like I think a month ago or something else. But yeah, let's get started. So, well, now you know, I'm Stefan, I'm developer advocate, so it's extremely bright. It wakes you up a bit. And I'm just going to talk quickly about Milvus. So, who doesn't know about Milvus? Okay, so some people know. That's nice. So we are an open source vector database. We're part of the Linux Foundation as well. And basically we can help you like from, you start your prototype with a pip install to then reaching hundreds of billions of vectors. Our biggest customers has 100 billion vectors. So that's usually the scale we're at. But we can also help you, with like your small project when you start in your notebook with a pip install. We have a lot of integration with basically everything. We support a lot of features. So we think we're the best, no bias here. And as I said again, we have like integration with basically everything. A lot of AI toolkits. We actually have someone talking from JinaCLIP this morning, and we have an integration with them as well. But we have integration with like, LangChain, llama-index, LangFuse, RAGAS if you want to evaluate your LLM. And then we have lots of other integrations. So you can check out the website directly. But that was it. That was the sale moment. So now I can actually go back into the technical part. So I'm just going to talk about the different components that I have, and then I'll talk about the basic of RAG, and then I'll basically explain why I'm using agents, why I'm using different models, and then I have a live demo, which hopefully should work. So I'm starting. So Milvus Lite, as I said, so we have Milvus that scales to like billions and billions, but then we have Milvus Lite. So if you want to start something, it's a pip install PyMilvus. You can write it in your node, and then you have to actually do it. And then yeah, so just pip install. But then I'm going to use llama index. So who doesn't know about llama index? Some people. Okay. So it's basically a framework to help you build your LLM applications. So it's really more focused on like retrieving data and like connecting with like other tools you have and integrating it with LLMs. It makes your life easier. It can usually be very useful if you start. If you sometimes you reach production scale, you might start to struggle with it, but at the beginning, at least, it's very, very handy. It has an integration with basically every AI tool there is. So this is nice. Then recently they released llama-agents. So it's basically allowing you to work with like agent as microservices. Like sometimes you would have agents and then they would do a task, but then, you can't really scale it up and down. You have to scale up the whole thing. With llama-agent, what it does is that you have your agent doing one specific task. Let's say, I don't know, check emails. And then at one point you receive a lot of emails. You can scale up and down this task in particular. You can have another agent that is going to be your rack system, actually, and then you can scale this one up and down instead of like scaling the whole thing or, like scaling the whole part where llama index is running. So it's quite nice. You have like a control plane. Then inside you have an orchestrator, which is actually your LLM, which is going to decide what's going to happen next. And then we send everything to a message queue. And then that's where this one was like, okay, this agent will start to do like your RAG search, or then this one will start checking your calendar. And that's basically the idea behind llama-agent. Spoiler alert, it's a really nice idea. Still not there, but we'll see the code there later. But in theory, it's very, very nice. Then for this one, I've decided to use Mistral AI. One reason back then when I did the demo, so like they just had released Mistral Nemo, which was a mid-size LLM. So for the people that are not familiar, like LLM can have different sizes, and basically like the bigger they are, the better they're supposed to be. So like ChatGPT, for example, has like billions and billions of parameters, which is what you see here. And Mistral Nemo had 12 billion. So it's like smaller. I can run it on my laptop. It's also been trained on working very well with like function calling and retrieval as well. And then it has 128,000 context length. So it's also quite long, which is very useful usually when you use it with agents. I'm also going to use Mistral embeddings, which also have been trained with a focus on retrieval. So it's also very useful for RAG. And then the only problem, though, is that it's English only. But for my demo, I'm going to do everything in English. So this one is fine. And then as the orchestrator, so the one that is really like, handling everything, making sure that you know what we're doing, then I'm going to use Mistral Large 2, which this one is 123 billion parameters. And again, it's like very strong on function calling and retrieval skills. So those are the reasons why I went with Mistral for this one. And then I'm also going to use Tavilai. So for the people that don't know, it's a web search API that is really used and helpful for LLMs. You can sometimes you could do it on Google and that works and that's fine. But then, it's not really tailored for LLMs. Well, this one is really made for LLMs. So then the results might look better and then the LLM will understand them better. And it's quite handy. So yeah, you should check them out. But maybe I'm going to go back to the basic a bit. So who doesn't know what RAG is? Who hasn't done it? Some people. Okay, cool. I have some slides for you, so it's fine. So the basic idea is to force an LLM to work with your data. Because what happens is that you train an LLM up to a certain point, and then you stop the training, let's say like end of August. So then everything that has happened after end of August, then you don't know what, the LLM doesn't know about it. And then if you ask also like data that is like a private data that the LLM hasn't been trained on, then it also won't know about it. So that's the basic idea of RAG. It's like you're really going to inject some data to your LLM, some fresh data or some private data, and then you can use it. And then you can have like basically a better system. That's the basic architecture. So you're gonna have, you're gonna have your data, then you're gonna extract the content, and then you're gonna do what we call chunking. So that's really like dividing the content into different parts, and then those are gonna be transformed into embeddings. So we'll have a way better explanation of embeddings as the last talk, but it's basically transforming them into vectors. So like just a list of numbers. Then you store them in your vector database. And then as a user, then you make your query and then you put it through the same embedding model. And then you do semantic search. We're going to return the similar data. We give it that back to the context of the LLM, and then we give you a response. And that's basically what's happening when you use RAG. That's the basic one. And it's cool. It works nice. If you use llama index, it's 5 lines, basically. So, you're loading your documents. You're going to like embed them and index them. Then you're going to generate your query. And then you can just ask questions. And that's, it's a 5-line software. So that's like, it's really cool. It's really nice. If you have private data you want to play with, then you should do that. It's cool, but it's also limited, it's like, it's basically only search. And, like, it's really like limited. It's like, it's only a one-way through, for example. So while it's nice, we can see like it has different problems. So, it's like single shot. Then it also has no query understanding, no planning. It doesn't know how to use tools. It has no reflection, no error correction, and also no memory. So while it's nice, if you're actually doing something in production, you might want to do something else. So that's where also like, also like summarization is really bad at. It's also like bad at implicit data. So like if, you need to find something on the internet that it doesn't know what to do with that, it's going to be like, okay, I just don't have this data. No idea what to do with it. It's also bad, usually, if you ask multi-part questions. So, he would likely not be able to, to separate your question into different parts, which Agentic RAG can do. So that's like a problem. So basically, it's necessary, but it's not sufficient. So that's the whole part of like basic RAG. And now, like for the past, I don't know, 5 months, everyone has been talking about Agentic RAG. And I'm going to give you a quick intro for it. So basically, it looks like that. And I'm very sorry. Every time we go from blue to white, the brightness is crazy. But that was not planned. But Agentic RAG is basically that. So you give your query to your agent, and then the agent will decide where to go. So it's like, okay, we're going to go to the RAG system, or then maybe I'm actually going to use another tool, which is a search, like, a search on the internet. Or maybe I'm going to check your calendar. If you're asking me, are you free today? Then that's basically Agentic RAG. What's cool is that it's multi-turn. So, you have your agent that then going to ask a tool, and then the tool can go back to your agent and then check if you have actually answered the question. Then you can also like, you can like, plan for some tasks and some queries. It also has like, you can actually use tools, for like the external environment. It has reflection. So it's going to be like, okay, actually, am I right? Did I answer the question correctly? So it has that as well. And then it also has memory for personalization. So, you can like actually talk, and then it will actually remember what you talk about. And it can do that for like a lot of users as well. So that's like the good part. So yeah, it also has self-reflection. So yeah, check the internet to verify if it works. That's obviously if you add this tool to your agent. But then it can also do like query routing. So, like whether to check your RAG system or not. But then if your query is also very complicated, what it can do is that it can create some subqueries. So then it's going to be like, okay, for this query, are we checking my RAG system? Or for this one, am I checking my RAG system? Or am I directly checking the internet, And then, yeah, it can use some tools and everything. And now it's the demo part. So it's always the part that is the fun part, because it's the part where last time I did a demo, it didn't work because LLMs are very nice. They're very glorious. But sometimes it doesn't work. So in this notebook, we're just going to get some data. We're going to store it directly into Milvus. Then I'm going to use llama index with Mistral, for like data queries. Then I'm going to create those data search queries automatically. And then I'm going to have an agent that is also going to create some metadata filtering automatically. Then I will do a web search. And then hopefully it should work. And then my agent will decide if it should do a web search or if it should check my vector database. Or then if I'm like asking a question that should combine the two, then it should actually combine the two. So let's go, let's get started. So as I said, I'm going to use Milvus Lite. So I'm just, it's just a pip install. It's what we have here, and that's it. I won't run it here because it will take a while. And because I'm using Mistral Large, I'm going to need to have the API key for it. And then also going to use Tableye, so I also need the API key. So I'm just loading those. I'm going to cheat a bit, and then I'll show you the data that I'm using. But I'm preparing, so I'm going to use Mistral embeddings for this one, which is the one that I mentioned, which is in English. And then I'm defining the LLM model, which is going to be Mistral Nemo, which is, it's running with llama, so everything is running on my laptop directly. And then this one is where I get the data. So basically, I have two files, which you might be familiar with. It's the financial data of Lyft and Uber in 2021. So I can just show you quickly. I won't bore you with the details because Lyft is 238 pages long, but it's just, about the stock exchange and, their performance and everything at the stock exchange. So I'm loading those, and like basically what I'm doing is like I'm chunking everything, putting them through the embedding model, and then loading them directly into Milvus. So we have it here. We can see like, okay, I'm doing it in this file, and then the dimension is the dimension of the embedding model, and then I'm just creating a collection. Then I'm loading my data, building my index, and then define the query engine. It's what I've seen before, but it's kind of like 5 lines, basically code. So that's like, we're happy here. We have like the basic of our rack system. And then now it's like where you do a bit of the magic. So here I'm going to define 2 tools. And those tools are really like, they're very, very specific tools. So there's one tool which is only going to provide information about Lyft financial data for the year 2021. And you can see it here. Like I'm writing everything in English, because that's how actually my agent will know what to do and when. So it's really like, okay, I'm really describing everything that it's doing. And like, okay, I'm even saying the company name. So it's like a very, very specific tool. I have the same for Uber that I have here. And, like it's the same, I provide Uber financials for year 2021. And I also say, please do not attempt to interpret or summarize the data. And then here, I can actually start, using my rack system. So this one is the basic one, where it's just going to be, I'm asking the question, could you please provide a comparison between Lyft and Uber in 2021? So what it's doing now is that, it goes through the embedding model, and then we're doing a semantic search. And in the meantime, it's going to check for everything in my data. And we can see, my agent is like, has 2 functions that it can call. It has the first function, which is called Lyft 10K. So you can see it called it, and then it actually give the input what were the total revenues for Lyft in 2021. And then it's the same one for Uber that you have here. And you can see first, it split my questions because, my questions technically had 2 in it. So then it's just been like, okay, actually, I'm going to check Lyft first, sorry. And then I'm going to check Uber. And it did that on its own. I didn't ask him to do it. Then you can see it has the output. And then it's like giving you like an answer, it's just like Lyft revenue increase, blah, 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 blah. And then Uber has like 17 billion revenue. And so you can see now, like the tool really like decided which tool to use and when. And that's like, it's quite nice. But imagine now, if you have, I don't know, if you have like thousands of companies, you don't want to create a tool that is going to be like thousands of tools. You want one tool that is then going to decide which search to do. Is it me or is it extremely warm in here? It's warm, right? Okay, because I'm next to the screen and I'm boiling, but okay, sorry. So basically when you want to do that, like let's say you have a collection with like thousands of data from 1,000 of companies. This collection can become quite big. So you can do what we call metadata filtering. And basically you can, like before doing the vector search, what you can do is really like, you can filter out already a lot of results. So if you're going to filter out, for example, directly on Uber, then you can filter out on that one, and then you can only do the vector search on that one, which is going to be way faster than if you were to do like the vector search on everything. And it's really useful, for like search results. It can also be used like better for efficiency, and then you can also customize, the search for like meet specific needs. For example, like if you want something from a particular year or a company. And for this one, I'm just doing it manually. So I'm just saying, okay, here is an example. I'm creating a metadata filter with a file name. And then I'm saying, okay, I'm only going to look at Lyft 2021. So then, I define like something very similar. It's the similar tool, but this one, I'm just saying different companies' financials for the year 2021. And I have my filter. And now if I call it somewhere, yes. If I call it, now it's actually going to only look at like Lyft data and not like everything. So if I ask the risk factors for Uber, it shouldn't be able to tell me an answer, except if it's hallucinating. But let's check. Nice. So it gave me an answer, which I know because I worked with this data a lot, is actually an answer of Lyft. So it's actually in the Lyft collection. This document is like this part, actually this whole part here. Everything here is about Lyft and not Uber. But because they're so similar as well, the LLM is like got confused. And then it's like, actually, I can answer something that is about Uber. So it's something that you have to be careful if you build some RAG system. Like, like this is a typical hallucination. It sounds true. Technically for Uber, I'm sure it's also very true. But that doesn't belong to the Uber data. That belongs to the Lyft data. And you can see, now if I ask the same question for Lyft, the answer, which is here, is basically the same word for word. And that's also how I know that, this one is actually in Lyft, and this one was not in Uber. So it's something that you have to be careful. And that's basically an example of like the LLM being confused and not knowing what to do. But now, I created a metadata filter on my own by hand. That's cool, but I want to do one that is automatic. So that's where you do like some prompt engineering. So, it's really like, I'm basically telling the LLM, hey, extract some metadata filters, consider like, I'm giving some examples, consider company names, the years, or any other relevant attributes. Don't write any other text. You really have to tell the LLM everything to be very precise because they tend also to be very verbose. And then I'm like, okay, so one-shot learning basically. So format it in that way. If nothing is specified, just return an empty metadata filter. I won't go into everything, but I am a dirty person. I'm using eval here, which you shouldn't if you run things in production. But for the sake of the demo, I'm the only one running that, so I'm fairly confident that I won't hack my computer. But then you can see here, I'm asking, what is the Uber revenue? I'm giving it a hint. So it's like something that you could do, if you were to have users, they could write something and then you actually reformat it and then you give hints to the LLM. So that's basically what I'm doing. I'm like, what is Uber revenue? And I'm like, okay, this should be in the file name Uber 2021. Then, automatically create this metadata filter with a file name and the value that is here. And now we can actually do the same. So it's like, okay, I'm defining a tool again. Nice, it didn't work. I'm defining a tool again. Yes, now it's working. And it's like, again, creating my metadata filtering. And then it's like, okay, we're going to search through everything. And then hopefully now, yes, it worked. So this one actually found out, in the data, I only looked at Uber's data, nothing about Lyft, removed Lyft completely from the search, and then was actually able to then find the data that's, Uber's revenue in 2021 was 17 billion. So that's like, it's just an example of like showing you, if you were to have a lot of documents in production, how you can like actually filter it with LLMs and without you having, to do like all the metadata filtering on yourself. But that's cool. But let's say you really have some users, you really have people using it. Then you might want to add, search and like internet search. So that's basically what I'm doing now. So I'm defining Tabuli search, which is the search engine. And I'm asking what's the weather in Paris. So this one, it returns us a very beautiful document that is very long. But you can see somewhere, yes, you can see somewhere, it has like the weather about Paris here. Where is it? Yes, it's partly cloudy. There is wind and everything, and then you could like format it to be like to look better. Like now, that's just the results of Tabelai. It's not very pretty, but at least like it gave you something that is actually real time. Now, what we can do is we can actually add it to our agent. So we had something that was only data from the past. Now I'm actually going to define, okay, I have my data from the past, for like year 2021. And I'm also going to define the tabulate tool, which I describe. And I'm like, okay, use this tool to search the internet for up-to-date information on any topic. So we define it. Now I have both of them. And then I can do the same, but it's going to give us like a very ugly answer again. But hopefully it should still work. Yes. So it still works. And now what I want to do is that I want to combine the two. So I really want to combine, like the weather in Paris. It's a nice question, but I don't really care. First, because I live in Berlin. And the second one was really, it's more like about real-time data. So I'm going to use an orchestrator now to then, pick the agent, and then it's going to like do everything on itself. And it should like, synthesize the results. And then we should be happy, So it's really going to have like, we're going to have like the orchestrator, which is going to be Mistral Large because it's like smarter. And then we're going to have different agents. And then we synthesize the results and then we give it back to the user. So just as a spoiler, in the title, I put llama-agent, which is really nice. And I really like the idea is that you define, basically you already define an orchestrator, then you define the different systems, and then you tell, hey, use those whenever you want to. So that's what you have here, I'm going to use my LLM. Then I have the message queue, which is, just to communicate to the different systems. Then I define all the tools. And then I'm like, okay, I have a financial worker. I have a search worker. So in theory, if you were to deploy that like on Kubernetes or somewhere, then you could scale them up and down like those specific workers. Now, the problem is that llama-agent is actually on pause. So you can go on the GitHub and they're introducing breaking changes. So like now I can't run the code, otherwise it's going to break. So the idea is really nice. And you can see I have my orchestrator, I have my control plane, and then I can launch, the different services. But I won't want it, run it, otherwise it won't work. What I can do is actually going back to using only llama index and basically doing what they're doing, but without using the different systems. So I have my prompt, which is here, which is really determine whether the following query is either financial or general internet search. And that's usually what the kind of prompt you do when you actually have tools to use. You're going to really explain what the tools are supposed to do, when you should use them. So you can get quite verbose, but that's actually the way it is now. So yeah, if it's about company financials, whatever, respond with financials, and otherwise basically respond with search. And I'm saying respond with only one word because I want to call only one function. So yes, then we process the query, and then it's really okay, if the agent to use is then the analyst agent, then I'm calling this one, and otherwise I'm calling the search agent. So yes, this one, this one is working. So we can see the queries. There was one query which was what were Uber's revenue in 2021, and then we have this one, it was 17 billion. Then we have what is the weather in Paris. We have this ugly document. And then I think I had asked another question, and then this one, it seems like it's not working. It's what were Uber's revenue in 2023? And this one, the LLM got confused again. It was oh shit, I thought I was supposed to look in my vector database, and then I don't have this data. So then it's gonna give you actually this one is I can't provide, I can't do it. So this one is actually it's actually telling you, okay, I don't have 2023. I'm gonna give you 2021. But if I go here, yes. If I go to this one, then this one, I have the same prompt, but then I just removed everything from llama-agents. And this one should work, actually. I'm really okay, either you have this tool, this company docs, this one is Tabelai, and then just use those, don't try to go complicated. And then I have 2 questions, which are, what are the Uber's revenue in 2021? And then I'm asking it actually to compare it to 2021 with 2023, which I don't have. And hopefully it should combine the two and be like, actually first search in the rack system and then do the search on the internet. So of the first one, we're happy, you know, it's a very quick search in Milvus. Nice. And the second one apparently didn't work. And that's the pleasure of working with LLMs. It won't work. So yeah, that was my demo. That was a failure. I'm sorry. It was working this afternoon when I did it. It was very pretty when it was like checking the data directly in Milvus and then, you know, checking with Tabuli and then combining the two. But it seems like this one didn't work. So yeah, I guess I'm gonna call it the demo effect. And I'm sorry that it didn't work, but I am gonna take questions now. Thank you. Do we have some questions? Here? Yeah. Taking longer now, so it might work. Shit, it didn't work.
When you say it doesn't work, if you run it multiple times, does it eventually work?
No, this one, I mean, usually for LLMs, it could, if it's only depending on you on the LLM. This one, I think it's because I actually run a cell where llama-agent was running. And so you can see like now it's just, like it's about the method of llama-agent that doesn't have an attribute. So like here is just a bug in the code. But sometimes it can be the LLM like not being able to actually find the answer or then understand the answer.
Thank you.
Other question?
There's any reason that you,
Yeah, sorry.
yeah, why did you choose Mistral AI and well, what's the reason?
The main reason was to use Nemo. So Mistral Nemo, you know, allows you like runs locally on your machine, and I use it with Llama, so it was working very well. And it's really good at function calling and reasoning, basically. So you know, like being able to call some functions. And yeah, that's basically it. Thank you. And Mistral Large was also like it's the bigger one and it's supposed to be better at like orchestrating. It's a good like in between, basically between like the 7 billions and the other ones.
Yeah. Hey, thanks for the demo. Thanks for the lecture. Pretty cool. I have a question. You skip pretty fast how you chunk, like how you store and then chunk and then how you retrieve. Basically, what strategies you by default using, and like how you decide what is best for your project.
I think it depends on the project. There's a lot of research happening at the moment. So maybe the last talk can talk more in details about that. But usually for me, it's going to depend on my documents. So if I have a PDF from like now, I basically chunk the whole page. Like one chunk is one page. Then I also have like a lot of metadata that I add actually, because that's very useful for the LLM. I'm checking more and more, you know, like CallPally, for example, you know, which is like visually, and then using, you know, vision LLMs as well. It seems like to have like pretty decent results. So it mostly depends, yeah. But yeah.
And overlapping between chunks, you also
overlapping chunks, yeah, a bit of like, I think my default one, I don't really go crazy. Like my default one is going to be like 256 with an overlap of like 50. And then usually what I like to do is actually adding, you know, like some chunks of like the above or like, you know, summary as well, like summary embeddings as well of those paragraph or of the document or of the page. And then, you know, add them all the time.
Okay, thanks.
You're welcome. Have one here as well in the front or there.
So I was just wondering what
Link graph, yeah. Yeah, so llama-agent is basically a competitor of LangGraph. It's like where they position themselves. I had better results with LangGraph in general, like, you know, actually building the graph and everything. But I think it's because it's the beginning of llama-agents. I think the idea of llama-agents will scale better, you know, actually having those microservices. But yeah, like they're basically competitor, you know, like if LangChain releases something, Llama Index have to do the same, basically. But Yeah, llama-agent is more like microservices. Yeah, yeah.
Have you ever worked with audio files or like any that kind of data sets or extracting it into text and then working on it?
No, I've worked with videos, but like more on like images, basically like sequences of images, and text, and just images otherwise, not audio yet. Sorry.
Thank you.
Also, it's not as warm anymore, so we're happy. Oh, we can do it after. Thank you.
Hi. We have many vector databases in the market. Why
Yes.
Milvus? Why another new one? And also how scalable Milvus is, and what is like.
How's the second? What did you say? Sorry.
Sorry.
What did you say for the second question?
Your vector database. Like I'm saying, there are many vector databases in
Yes.
the market.
Yes.
Why there is a new one? What is the special features that you have that you thought,
Yes.
okay, we need another new vector database?
Okay.
And then observability of this vector database, like how I can monitor the search performance, like the recall precision, something like that over the time. Is there any way it exposes some metrics that I can monitor over the time?
So first question, technically, I guess we're new in Berlin because I've been there for like 7 months, but the company is from 2017, really big in the US and in Asia. So we would technically not a new one, but to answer your question, why another one? And what's our strength? Usually our biggest strength is scale. So as I said, like our biggest customers have like 100 billion vectors. I don't know that many vector databases that can do that. And then another part is like we're fully distributed, so like it's really like every component can be scaled up and down. And the third part, and I'll stop here for the sales speech, but the third part is like we can basically rebalance everything live. We don't have, if you have somehow today you have 10 million vectors, then tomorrow you add another 10. You have to rebalance everything. And the way we do it is that we have very small sections, which are called segments, and then we can just balance those kind of everywhere. So then you don't have to recreate a cluster, which you might have to do, with like some of our competitors. You have to like clone the collection and then, like create some shards before. You have to know the amount of shards you're going to have. Like for us, we just do that live. And second question, for monitoring, we push a lot of metrics through like that are like compatible to like Grafana and everything. So then you can get those, for example, if you have like, but those are mostly like, software engineering metrics.
Yes, but besides that, I was more curious to know how I can measure the search performance. So for example, if I want to evaluate two different vector database,
Yep.
why I need to go to Milvus? So the current in the market, from my experience, what I see that some basic metrics about like recall precision.
Yep.
When we try to evaluate different vector database, it is very difficult
Yes.
to get those metrics. So especially for enterprise company, it is sometimes very difficult to say the stakeholders that okay, Milvus can be suitable for our use cases because we don't have the metrics.
Yeah.
So if we, for example, use Milvus, then can we continuously monitor that, okay, over the time when we have many data coming every day, over the time our search performance, I mean the recall precision is getting also in a balanced way, like we are not losing any performance.
I don't know if we expose those to Grafana directly, but I know like a lot of our enterprise customers would have that. And to answer, I'm going to do like an LLM. I'm going to divide your question into to answer the first part. We also have an open source benchmark tool that you can use, and then we have like support all the vector databases as well. And then you can, really like, if you want to compare us to like Weavegate, for example, or something, you can configure it yourself as well. So it's not like, we don't put our bias as like, we put like really shitty values for them so we look good, It's just you can see like all the configuration files, and then you can compare it. And then I think we use it like we have different data sets as well that are available. So it can be like, Cohere for the Wikipedia embeddings, like, 10 millions, 100 millions. I think we stop at 100 millions. And then we can, you can check like different indexes, and then you can check if like the record and everything is then pushed there, for example.
Okay, thank you.
Thank you.
Hey, do you sometimes take any measures to fight those hallucinations that we saw?
Yes. So usually not in this one, but like in another code that I have, I'm actually using my LLM to check on itself. And people are usually very surprised, but it's like if you use an LLM and then you know the answer, and then it's like I do it actually with like ChatGPT, for example, and then I'm like, it gives me an answer. I know it's wrong, and I'm gonna be like, "Are you sure?" And then it's like, "Oh, actually, I'm very sorry. I'm deeply sorry." You know, like how it is, and then it actually gives you the right answer. And like usually by doing that, I've seen like a lot of positive results. I was really like, yeah, like check. And then I'm checking if that's fine. And then the second one is like, oh, have I actually answered the question of the user? And usually they introduces them. Thank you. All right. So the good part is that I'm still hosting, but now we have someone else on stage. So we will have the journey of large language models at GetYourGuide by Meghana. So please clap.
Good evening, everyone. So it's been almost 2 years since ChatGPT is released, and almost a year and a half since we started using them in GetYourGuide. My name is Meghana, and I'm going to share with you all the experience we had with using LLMs so far in our company. So the agenda goes something like this. So I'm going to introduce GetYourGuide first, and then talk about how we are structured, and then getting into the core of the talk, the use cases that we have. And then I'm going to dive deep into one of them and close with challenges and conclusion. So who are we? We strive to unlock the world's most unforgettable travel experiences. In short, we are a travel marketplace where we connect customers and our activity suppliers globally, and then we do it through our websites and mobile apps. So I'm part of a team called Machine Learning Platform, and we are a subset of broader org called Data Products. We deliver stuff like ranking, personalized recommendation, and so on. And as part of Machine Learning Platform, our main mission is that we empower teams to do so by advocating MLOps best practices and providing tools so that they are empowered to do so. So let's talk about the use cases. So we've had a couple in the content generation category. So the first is localization, where we'd like to translate our blog posts into various languages. And then we have had the AI-assisted tool creation for our suppliers, where we have used AI to accelerate their journey in creating new activities on our platform. And then we have had the FAQ section, which was newly published, where post-booking, there's a new section in your bookings where you can see the most common questions and the answers to all of them. So this has also reduced our contact rate significantly for our customer care representatives. And there are also these projects called novel trip items. As in when we have new activities in our inventory, we have to identify the new kind of product categories and also kind of add them in a way that they're contextual to kind of that region, the culture, and so on. And this improves our customer experience in a way that they can navigate our inventory better because they get more relevant search ads when they look for things to do. And the list goes on. So what's the role of ML platform in all this? So the ML platform, aka me, we have developed tools for all these teams so that they are able to do it and in a scalable way. So what are these tools exactly? So as part of the ML platform, we have developed something called ML service templates. which means there are a set of tools which help teams to jumpstart on their journey into going to prod by provisioning various infrastructures, all the tools, and also codified best practices. So this has proved quite scalable. By using these templates, teams are able to more reliably ship products within our organization. So let me go deeper into the use case, one of the use cases, which is for the localization. Here, we want to translate Explorer articles. So what are Explorer articles? So in GetYourGuide, we have a section where we have blog posts on various tour locations, for example, Hawaii. And then there's a travel expert who writes blogs on this. And then with the blog posts are also attached the activities. And based on how relevant they are for our customer, we get conversion. And this is the before and after of localization, of localizing one of these articles on Hawaii. So seems pretty straightforward, right? We just have to translate it. So yeah, what do we choose? DeepL, ChatGPT. But the answer is to use both of them. And why? So as part of localization, not only do we need good translation, but we also need to maintain our brand guidelines, which means we have a specified tone of voice and some brand terms that we are allowed or not allowed to use. And yeah, and for this, we need to use ChatGPT because it has the potential to do that. But why do we need DeepL? Because our localization team have prototyped this and found that the performance of ChatGPT in other languages, apart from English, isn't that great. And part of the reason is that most of the articles that we have online is in English, and European languages is like just 32% of them. For example, Spanish is 6%, so you can imagine the content that was used to train ChatGPT. And the vice versa is also true. We do need DeepL because DeepL has proved to be more performant in that aspect. So now we have a prototype. So how do we scale? At GetYourGuide, our tech stack looks something like this. So we have Databricks where we have our notebooks, and then we also run batch jobs. And we envision localization also to be kind of like a batch job. So that's why we run it in a long-running kind of a basis every day on Databricks. And then this is the templates that I talked to you about, where we have also integration with OpenAI, and we kind of wrote in-house optimizations to make it more efficient, and also organization-specific organization of prompt templates. And we also use Airflow to automate end-to-end the post-editing. So the process of localization, we call it post-editing. And then we have our own Datadog dashboard, apart from the OpenAI dashboard, because it gives us higher level of granularity and also organizational level, better organization in terms of looking at costs at an org or a team level. And for model evaluation, we use Arise Phoenix, which I will get to in a bit. So this is the end-to-end kind of how the process looks like. So we use Content Stack for the content where the English blog post comes in, and then we, over the API, we send the content over to DeepL for translations, and then from there we have our Airflow job, which picks up these files to be translated from Databricks storage. And then we have a tech team helping us who will publish this back to Content Stack. Right, now we have the post-editing working. So how do we ensure quality? From DeepL perspective, we have been using it for a long time, and we have no reservations about its performance. However, ChatGPT, we have had long-standing experience with hallucinations, especially like making up new places and times. In this example, we asked it, what are Istanbul's best evening activities? And we just wanted it to translate this, but ChatGPT kind of made up its own answer instead of just translating the question. And also, we've had prompt leakages, like we do include delimiters in our prompts to specify a portion of text that we want to translate, but the output also contains these delimiters, which are not ideal. And also, ChatGPT fails to remain in its role, and it starts commenting on the task itself rather than just playing the role. We've been using model graded or evals for evaluating LLMs. So this is inspired by the OpenAI evals. So it's also a recommendation from OpenAI, the idea of using AI to evaluate another AI. And this has been working pretty well for us, and it's kind of close to a standard that we're adopting in our organization, where we provide it with a background, and then with an input and an output metadata task, and then also an output format, in which we indicate the prompt to output either a good or a bad output. And then we send this data over to Arise. So this is our model observability platform. So if it's a yay or an A, all these gets recorded in Arise, and based on how good they are, you get a score. And coming back to evals, Arise also has an open source library called Phoenix. So they have some out-of-the-box evals for you to try if you're working on any of these use cases, like RAG retrieval or like QA summarization. You can use these evals out of the box. But what they also have very interesting is an option to create your own custom eval, which is what we did. And we leverage the framework basically to perform this evaluation. So yeah, now this is the end-to-end process, which I explained, but now with the evaluation. Right now we are quite aggressive. We are evaluating the whole data set, but over time, as we gain more confidence, we are going to do it on a subset, and hope to do it less and less over time. And we also do involve some of our freelancers. I mean, the main impact of this project was it was too much load for our freelancers to translate every single article. This project has also saved cost in that term, but we still do have like some freelancers who kind of look into the flagged articles and then either correct them, or we are also exploring options to do that automatically as well. So all this come with challenges. So the landscape is evolving quite rapidly since the time we started the project to when we actually finished it. There are many tools and frameworks out there which came out, which we couldn't like have the time to migrate or adopt. And prompt engineering is time consuming. There's no about that. And the evaluate prompt even more. And ensuring quality. So your prompts and your data become obsolete over time. And the model that's out there, they keep upgrading. Like you had like GPT-4 a few months ago, now you have 4.0, and then something else come up, and then the performance might not be the same, which means you need revisiting. And like I talked about human in the loop, so we can reduce the dependence on manual effort, but we cannot eliminate this completely. And of course, we've had organizational challenges. Like before we had our own silos, business and data science, we all worked on our own tech stack, or we did our own thing. But with prompt engineering, we had to collaborate quite a lot. On the tech side, we had more idea about, hey, how do you optimize your prompts? How do you structure the output and JSON versus like, more knowledge about prompt engineering best practices. But the business teams, they had a better idea of what exactly needs to go in the prompt, like the actual content. And we could see also our team boundaries kind of dissolving, where also these teams kind of stretching themselves a little more to actually writing some Python code. So yeah, there were like some challenges, but yeah, in the end, yeah, it worked out. But what we are also looking into is kind of organizationally making these teams quite decentralized in a way, kind of providing training so that they can also be kind of independent when it comes to LLM. But this is still an experiment, and yeah, we have to see how it goes. So that's it for my talk. So I'm going to hand over the mic for any questions.
Do we have one there? Okay, I'm coming. It's a big space.
Yep. Thanks for the talk. It was great. I have one very pragmatic question. So you mentioned that you would using the Databricks jobs to run the workload. Well, we all know Databricks is great for experimentation, notebooking, collaboration, and other things, but it's super costly. So my question is, why did you choose it over the cheaper options which are available, since you are using, for instance, Airflow? You can use it with Kubernetes or whatever.
So we use Databricks for experimentation and also batch jobs, like anything which is like long running. So we need like batch jobs, which I mentioned. But for online services, we still use Kubernetes. That makes sense.
But that's exactly the question. Why you use Databricks for batch jobs instead of just Kubernetes or EC2s or whatever?
I mean, that's like a broader organizational question. I mean, for data science, I think it's easier to have like your own cluster and tear down. I think it's also, easier to like manage it. I think in general, it's like a fewer people having to maintain this cluster for you versus already like a managed service. And that's like a decision, kind of like an organizational decision.
Just follow up question. How many people are in the ML platform team?
Sorry?
How many people are in the ML platform team?
One.
Maybe also that can be a reason. Thank you. Any other questions? No? No, it's just, you're just chilling against, okay. Oh, there. No one here? No, okay.
Okay, I have a very common questions that why ChatGPT? Why not other LLMs? What was the problem with the other LLM and why ChatGPT?
I mean, we tried also fine-tuning our own LLMs, but we had like so many use cases that we need a dedicated data scientist to have to do this. And comparing the cost of a data scientist versus cost of running prompts in a job, cost of running prompts in a job is cheaper versus the time of the data scientist.
No, I mean, ChatGPT is a vendor, right? So you are using ChatGPT, so not in-house LLM. So there are other LLM out there. Why ChatGPT not? Why not like something else like Cloudy, for example? Why not other LLM model?
Yeah, I mean, that's what I said, right? So that's also the challenge that once we start with this, then many new tools come out there. And then oftentimes we don't have the capacity to move away from what we started with, because then again, you need to evaluate this and maintain your model performance. And then you need to it's kind of like starting from scratch again when you shift to another model. So of course, you can try to evaluate, but it's usually like in the beginning of your project iteration where you decide on a model, you do your prototype. But at this point, we did a like prototype with ChatGPT, and the prototype was good. And then we didn't want to change it again during our in mid process.
Yeah, thank you.
Thank you.
Thanks for the talk. One question related to shots. So not alcoholic shots, but like more, how much shots do you think you have to train the models on to, like not train the models, you have to get to get good results? Do you think it is related to like when we were back in deep learning, people said add more layers to just increase the accuracy, and right now it's like adding more prompts to get a result? How do you deal with accuracy of the model when you have to serve millions of users? And what is like your strategy on that?
So for us, performance is not really a concern because this is an overnight job. And yes, by adding more like one-shot or multi-shot LLMs are slower, but the use case is, like I said, is batch, which means our job runs overnight, and tomorrow morning a new article is published. And so, yeah, in this particular case, we don't want like an LLM to respond right away.
Thank you. Any other questions? Yes, here. I'll start here, just closer, and then I'll come to you.
I'd be interested in what kind of KPIs are you looking for during the evaluation? Because I've seen, for example, in the OpenAI cookbook for RAG systems, there's like these log props which you can calculate into like relevance scores and then just evaluate on that, for example. So what kind of KPIs do you use?
Yeah, we're keeping it pretty simple for now. We are using precision just because it's also our business teams that are looking at this. And we kind of have like a threshold of 8 to 10% where we can, where we allow room for like hallucinations. So of course, the same time, the same prompt 2 times may yield different results. And we know that, and we have accepted that. So 10% of variability is what we can accept. So till then, if our threshold crosses that, then that means we need like a manual review. So there's nothing more sophisticated over that. If it's like more than threshold, then we have manual reviews.
So I understood this as a very specific business case. How would you measure the traction rate of the articles or contents that it generated automatically compared to human-generated content?
So there's like a SEO team. So I think like the end metric that we are looking at is number of visitors. I think that's one of the metrics that we're looking at. And ideally, we want the visitors number on our new articles. And since these are newly published articles, I mean, these articles were never there before. So for example, you never had an article in French. So even if you get 1 visitor for French, so that is still a win. Of course, there can be like ways you can still experiment beyond this, like how you can, how further can you make the content so that you can increase it. But at this stage, we just focusing on getting new visitors for these languages.
Thank you so much.
Thank you. Thank you very much again. Thank you. Thank you. Thank you. We're gonna have a small break so you can get a drink and stuff. I don't think we have any food left, but the drinks on the right side go because I think it's very warm. And we'll be back in like 5 minutes or something. Thank you. All right, so you're gonna start. All right, so we have our third and final talk of the night. So it's from Clip to JinaCLIP. Jina AI is an amazing company. So I'll let Bo talk over. Thank you, everyone.
Thank you, Stephen. Hello, everyone. Thank you for having me here. I'm Bo. I'm Bo Wang. You can just call me Bo. I work for Jina AI. And today I'm going to present you our this one, from Clip to JinaCLIP, training the general text image representation for search and multimodal RAG at Jina AI. And this is actually largely from our recently published paper. And so this talk will be largely describing this paper content, and it also a little bit beyond that. So let's go back to some very basic questions. What is a good embedding model in your case? Because embedding model search is the key for the RAG, and a good embedding model, I believe, is the key for your success of your RAG applications. And in my mind, a good embedding model should have very general good performance on a variety of domains. without fine tuning. So a lot of people do embedding model fine tuning, but I believe it should be generally trained. And a good embedding model should also connect left and right. Left could be question, right could be answer, left could be I don't know, query, right could be document, and reflect it with a higher cosine similarity score or whatever score. And embedding model does not necessarily be text only. And here I'm referring to sometimes most widely used modalities, such as text and image. And so a lot of the conversation will be between text and images because it's a clip. And I will discuss a little bit text image search in the old days. So basically before the OpenAI clip model. And because text and images are from different modalities. So connecting different modalities is very hard. So first of all, there is basically no way for you to search text from the image. So you need to really manually kind of convert an image into text. Either you do it manually or you build this conversion based on some hypothesis. So previously, before the OpenAI clip was released, people, for example, if you're doing this text image search on the social media websites such as Flickr, Instagram, this Flickr will allow you to tag in these images. So it's basically creating this conversion between image modality to the text modality. Also, the Instagram allow you to add a text description of this image to make this image searchable. Imagine there is no user tagging. So some people in the research community, they try to build some hypothesis. For example, if an image is surrounded by some text, so people just hypothesis this text basically describes the image it's being surrounded by. So this is the way how people search text from image. And in some modern days, such as 2010 or 2015, something like that, people started to train classifiers. So people started to train maybe object recognition classifier or classification classifier and try to manually tagging the images based on the classes, such as a car or whatever. But it brings very unstable result and very poor out-of-domain performance. For example, your class is not being trained, your training data, then the model basically don't know what is it. And then OpenAI clip basically published. It's a very kind of simple, but also innovative and beautiful way to train a model. So you have text as training data, you have images as training data. Text and images are basically, text are basically captions of images. And each caption basically corresponds to each image or describe to this image. Then you have this text encoder, which can convert this text or image captions into an embedding. Then you have image to send into the image embedding, the image encoder to convert it into embeddings. Then you do this contrastive, what we call clip loss. Then you do the backward to update the model gradients and make the model learn. This is basically how the OpenAI clip trained. OpenAI clip is quite a breakthrough, but also nothing new here. So the training paradigm is quite old. So what you are doing is basically you are aligning the text and images. You are doing the text image alignment. And the loss function is also quite mature. So this is basically temperature scaled cross entropy loss. It's basically classification loss, like you train an image classifier, but it's bidirectional. We will come back to this later. The only thing really matter to make OpenAI clip work is surprisingly simple. They train on a large scale. So they train on 400 million text image pairs, which no one has done this before in the past years. Then the text image alignment suddenly works. This is a diagram I plotted using JinaCLIP. It's not exactly OpenAI clip. So on the left and right, on the upper diagram basically shows a UMap project embedding because we want to visualize into two-dimensional space. So there is green and blue dots. So each green dot is basically a text or image. Then each blue dot is a text. So there is green line connecting each image and text. Basically tells you this text describes this image. So you'll see before any training, the connection is quite masked. Then this is the second diagram, which in the below is basically after the model is trained. You will see the green dots and green dots and the blue dots are very beautifully aligned because after this clip style training, the two modalities can be aligned together. This is what we call multimodal alignment. And this is also something bad about CLIP. There is something needs to be improved. So what we call CLIP is an embedding model, also not. So CLIP has very strong performance on connecting text and images. So you can basically encode a text into embedding, encode an image into embedding, then do the cosine similarity between the text embedding and image embedding. Then you can rank based on the similarity. But this is also quite bad because CLIP can barely modeling text. Let me show you some numbers. So this is our internal evaluation. So this is some evaluation on the sentence semantic sentence STS semantic sentence task. So basically measure how close two texts are close to each other. There's some leaderboard on MTB. So you will see we basically encode text pairs using the CLIP text tower, basically getting the text embedding from the CLIP model. Then we compare the result with a properly trained embedding model called JinaCLIP embedding v2. And you will see the gap is actually quite large. So JinaCLIP v2 on this task get an average score of 80.7. Then the CLIP text tower or CLIP text embeddings gets 66.22. This is even worse if you compare in the search domain, because the previous datasets are all like short datasets. And here, the datasets are much more, how can I say, asymmetric. The left side is a query, the right side is a long document, or the left side is a question, the right side is an answer. So the dataset is much more asymmetric. So you see that the CLIP text embedding barely works. So it can match around 30% the performance compared to a properly trained text embedding, such as JinaCLIP embedding v2. So this is the reason why CLIP cannot model text well. So during the CLIP training or the OpenAI CLIP training, the text was basically truncated to 77 characters. So if your caption is longer than 77 characters, it will be basically ignored. On the second part, most of the CLIP captions or the CLIP caption of the images are very short, such as this is a picture of dog, this is a picture of car or whatever. So this model is not able to learn basically giving such short captions. The third reason is there's no guidance by hard natives. When training a text embedding model, normally there are like two stages. The first stage, you have the text pairs, and your training objectives is to bring close these text pairs. Then there's the third stage, which is called triplet training. You have the text anchor, and positive and negatives. So your objectives is to bring close the anchor and positive, and pushing away the anchor and negatives. And in the CLIP style model training, there is no guidance by the hard natives. So the model just cannot search texts. And according to some paper, why the font is so small? So there are some paper called llama-agents. Basically, they did some experiment and they verified that so the CLIP text embedding can only encode around 20 tokens. So beyond 20 tokens, CLIP cannot do it well. So we, based on the fact that CLIP text embedding doesn't really work. So imagine you are building a multimodal RAG application, and this is how you search. At indexing time, you have text and images. So you first try to encode the text and images using the CLIP text encoder and the CLIP image encoder separately. Then at searching time, your user query is normally a text. So what happens is you are trying to encode the search query using the CLIP text encoder, and you do the cross-modality search to search for the associated images. On the other hand, you want to not ignore the text from your dataset. You do this unimodal search from the CLIP text embedding to the CLIP text embedding, which you indexed. Then this unimodal search won't work. The cross-modal search will work because the CLIP text tower is such a weak text encoder. So at JinaAI, we figured out this reason, and we decided to train a new model, something called JinaCLIP. So basically, we want to, if you want to do the cross-modal search in the real life, you have to maintain another properly trained text embedding model to do the unimodal search. So we want to simplify this. You have one model, which is called JinaCLIP. This model, at indexing time, you're indexing text and images. And at searching time, you basically give the user query and encode into text embeddings. Then this text embeddings produced by JinaCLIP can do the cross-modal search and unimodal search. That is JinaCLIP. Some very basic statistics about JinaCLIP. So the model is actually quite small. It's around 200 million parameters. And we trained this model for 70K steps on 3 stages total, but you will see that later. And for each step, we are training with a batch size of 32K. And so the model have been seeing 2.3 billion text image pairs. And on the other side, we are also training the text encoder. So on the per step, the model is also seeing text-text pairs or text image triplet, which has a batch size of 32K. So the model for each batch basically says 64K text or text image pairs, which basically seeing around 5 billion text image pairs or text-text pairs. And this is trained on NVIDIA H100 for 1,600 hours. This is basically how the CLIP model was trained. You have seen it. You have text, you have image, you have text encoder, you have image encoder, do the CLIP loss, do the backward. And this is how JinaCLIP was trained. It looks like a little bit complex, but it's actually stupid easy. So they are basically, you can ignore the stage 2 or stage 3 right now. You can first focus on the task 1 and task 2. So you know that OpenAI CLIP is basically optimized for, let me come here. OpenAI CLIP is basically optimized for this part. You have text captions, you have images, you are doing the CLIP loss, and you do the backward. In JinaCLIP training, we basically add another task called text embedding alignment. So you have text here, you have text here. You send to the CLIP text encoder actually here. Then you do the competitive loss, quite similar to the CLIP loss, but works for text. Then you summarize these 2 losses and do the backward. So in the training stage, you are basically optimizing both the text encoder and the text image alignment. You are basically optimizing 2 tasks, but there are 3 stages. So the first stage is something what we're discussing now. The first stage basically trying to make JinaCLIP works very well for the cross-modal alignment. But we also want to warm up the text embedding model a little bit. So you will see the evaluation result. This is basically on the retrieval tasks. After the JinaCLIP stage 1 training, the performance of the text embedding basically doubled from 21.53 increased to 43.40. Then we officially go into the second stage, because in the first stage, we are trying to warm up the text embedding, but we are also trying to use very short captions to make the batch size very large. In the second stage, what we did is we basically removed this 77 captions limitation. We try to make this model train on much longer context, such as 512 tokens. And we also prepared something what we called long captions here, because normally CLIP captions are quite small. And we prepared very long detailed captions to the images. And this is basically the second stage training on much longer context, training on much longer context captions. And we do the same like stage 1, but optimizing 2 tasks in parallel, like text embedding alignment and text image embedding alignment. And you will see after stage 2 tuning, after we enlarged the context length, the model again improved like 2%, something like that. But still, we have a like 10% gap compared to the JinaCLIP text tower and Jina embedding V2 base. Then we finally go into the third stage. Remember previously I discussed, because the text embedding models are normally guided by the what we call hard negatives. So here we basically, this part is the same. We have long captions and images sent to the text encoder and image encoder, trying to optimize the CLIP loss, doing the cross-modal alignment here. But here we are giving the query document and hard negative document. Our objectives is to push these 2 parts closer and push away this query and hard negatives. So letting this model can distinguish what is a good match, what is not a good match. So we are basically doing this. This is the only thing changed in the stage 3. I wait for your picture. And the final result is basically like this. After the full training, this JinaCLIP stage 3 is basically the final released JinaCLIP. And the text embedding performance of JinaCLIP basically on par with the JinaCLIP v2 based embedding model, our previously best in-class embedding model at Jina AI, measured by NDCG at 10, which is quite nice. And remember, we only discussed about the text embedding performance, but how about the overall performance? Because the key of OpenAI CLIP model is it can do the cross-model alignment. So you'll see we measured some performance here. This is, we changed to record 5 because most of the text image search measured by record 5. So here, if you see the performance of Jina embedding v2. So because it's a text-only model, so the text search performance is quite good, but it cannot do the image-to-text image search or image-to-text search. There's no like vision capability of JinaCLIP, a Jina embedding v2 model. On the other hand, if you go to the middle, this is the OpenAI CLIP model. It has very weak performance on the text-to-text search because the query type is text and document type is text as well. But it has very good performance on the cross-model search. If your query is image, document is image, it's good. If your query is image, document is text, it's also quite good. And this is basically JinaCLIP on the left side. And the JinaCLIP basically text tower improved compared to the OpenAI CLIP for 165%. And this is not only about text embedding. If you look at, you want to do the text image search, JinaCLIP also improved like 2%. If you want to do the image text search, maybe no one do this, but JinaCLIP improved like 6%. Most surprisingly, I don't know why, but if you do the visual embedding produced by the JinaCLIP image tower, do the image similarity search. So JinaCLIP also produced very good, very high quality image embeddings. Compared to the OpenAI CLIP, it improved like 10% to 12%. And remember this image? So before the training, the alignment, cross-model alignment is quite a mess. Then after the training, it looks very beautiful. However, there is also some problems. Maybe you see why there is a huge gap between the text embedding and image embedding. And this two semantic space is basically disconnected or disjoint we normally see. And this is the second topic I want to discuss in the talk, which is called modality gap in the multimodal embeddings. This is something I observed previously. I was using JinaCLIP because this is the only CLIP model you can do the text search and cross-model search. I tried to compute cosine similarity between some text pairs and do the cosine similarity between text-image pairs. What you see that the text similarity, cosine similarity, remember these are all like positive pairs, which means they are labeled as pairs, semantically related pairs. The text embedding similarity is centered around 0.7. So you do a text-to-text search using the CLIP text encoder, JinaCLIP text encoder, it will be centered around 0.7. Then if you do a cross-model search from the JinaCLIP text embedding to the JinaCLIP image embedding, the cosine similarity is centered around 0.7. But both of them are positive pairs. Why there's a huge gap here? So based on the cosine similarity. And we started to investigate. And this part is from another paper called Mind the Gap. So why modality gap exists? So first of the reason is the coin effect. So the gap already being created when you initialize the weights. So the model weights is never being trained and the gap already exists. So to verify this experiment result, I basically started this OpenAI CLIP again and basically randomly initialize the weights from scratch. And you will see the gap already exists at the model initialization time. So this is something we cannot change because it's basically from a text transformer and a vision transformer model. The second reason is what we call temperature-scaled cross-entropy loss preserve the gap. It's actually also quite easy to understand. So this is how the CLIP model was trained, how the CLIP data looks like. So on the left side, you have image 1. On the right hand, you have caption 1. So these are like pairs. And during the training, we basically consider image 1 and caption 1 as the positive pair, and image 1 and caption 2 to caption 8 as negative pair. basically we are trying to connecting image 1 and caption 1 and trying to push away image 1 against all the other captions in the batch. That's how basically CLIP was trained. Or you can consider it's a classification problem. Imagine you have image 1. Which caption is the correct caption of image 1? It's basically an 8-class classification problem. So if you look from the left side, given caption 1, which image is the best representation of caption 1? So this is basically what we call bidirectional classification. You can use image to classify the captions, or you can use captions to classify the images. So this is basically how the CLIP model was trained. But there is one variable here called the temperature. And this temperature has been proved to improve the OpenAI CLIP model a lot. So if you see here, there is something called logits equals to cosine similarity between left and right, then divide by the temperature. So if the temperature is 1, so basically nothing happens. If the temperature is, let's say, 0.01, so which basically means the logits of CLIP was upscaled by 100 times. So this temperature value is something we set at the beginning as an initial value, then this value is learned by the model itself. This is quite important. Normally, based on this paper, normally a higher temperature value in the contrastive loss function helps smoothing the similarity scores, reducing the overconfident and encouraging more uniform distributions. This is how the temperature changes when we are training the JinaCLIP in the stage 1. So we will see that the temperature value is actually started from 0.007. This is the value we set by ourselves. Then during the model training, the model automatically tries to pick up the best temperature it should use. So it gradually started to decrease. Then after 60K steps, so the JinaAI CLIP stage 1 was trained for 60K steps. The temperature is basically decreased to 0.01. So at first, at the initial starting point, the logits is basically scaled up to 13 to 14 times. Then at the end, the logits was scaled up by 100 times, which is quite large, which basically tells us the model is becoming more and more confident about its distribution, about its predictions. And it's becoming more and more confident and trying to make the prediction much more narrow than this wide smoothing distribution. And to verify this hypothesis further, we basically continue to fine-tune JinaCLIP for 5 epochs, so on a very small data set. In this time, we basically disabled the model to learn temperature, but we set a very large temperature, which is basically 0.1. 0.1 here is basically a very large temperature value. It's even larger than the initial starting point. So you will see we keep like plotting the cosine similarity distribution between the text embedding match and text cross-modal embedding match. Then you will see these two distributions started to have more and more overlap with this higher temperature. Basically tells us this higher temperature value can help us close the gap very nicely. But also because this temperature is chosen by the CLIP loss itself, which basically means that if you re-evaluate on the every batch, every epoch, the performance suddenly dropped to a very low value. So this is actually destroying the CLIP model performance. So when you want to fine-tune some CLIP model, better to choose a proper or let the model learn the temperature by itself. Do not try to close the gap by making a very large temperature value. And the third reason of this modality gap is it exists. That's why we call temperature scaled cross entropy loss preserve the gap. The third reason is something we call in-batch false negatives, stressing the gap. And I will show you why. So this slide. So previously we introduced that giving image 1 and caption 1, these are a positive pair. Image 1 and all the rest captions are negative pairs. CLIP is trying to push closer the image 1 and caption 1 and pushing away image 1 and all the rest captions in this batch. So what happens if caption 8 is a better description of the image 1 compared to caption 1? This is something we call false negatives. So we at Jina, we intentionally manipulate the training data a little bit. So there is a data set called Flickr 8K, and there's a bunch of text and image pairs. And each image has 5 corresponding captions, and we only use 4 here. And this data set is in sequential order. So during the training, we normally load the data set using the PyTorch data set, then perform some random sampling to choose a batch of data sets and send to the PyTorch data loader and let the model train. Here, we basically did something stupidly simple. We disabled this random sampler and used something called a sequential sampler. And this is how, after manipulation, the dataset looks like. So you will have something like this. You have image 1 and image 1 caption 1. Again, you have image 1 and you have image 1 caption 2. So we manually or intentionally created something called in-batch false negatives. Because caption 1, caption 2, caption 3, caption 4 are all the description of image 1, but here they are being considered as in-batch negatives. So we call it false negatives. So giving this way, if the batch size is 16, basically we are creating like three false negatives per batch. Then the rest of the 12 negatives are correct negatives. If you consider bidirectional, so basically we are creating six negatives, giving a small batch size. And we started to train 2 random clip models from scratch. It's a very small scale training. The only thing we changed is the sampler. So we have this sequential sampler basically creates a lot of in-batch negatives, which a lot of captions is a better description of the original image, but considered as not negatives. And we have this random sampler, which basically minimizing this effect. And we started to train this model with exactly the same hyperparameters. Then we try to evaluate the cosine distance between the text image embedding. You will see that the run with in-batch mismatch or with in-batch negatives has a much larger cosine distance compared to the one without in-batch negatives, which basically tells us that in-batch false negatives strengthen the modality gap. So there are basically 2 takeaways from here. So first of all, do not use the clip text embedding for text search. Then you will get very trash results. The second one, you need to really carefully merge the scores when you are doing the multimodal search. Especially, you need to carefully merge the scores for the text-image similarity and text-text similarity because they are just in different scale. And to use the Jina AI embeddings, it's actually quite easy. You just send a curl command or use the PyTorch request or whatever. Just do the input and you will get embeddings. You can send in text or send into images. And if you are using the Milvus database, you basically only need to utilize the Milvus multi-vector search feature, which is quite nice. So basically you import your Milvus Python client, connect the instance, and basically create fields, which involves 2 vector fields, which is called JinaCLIP text vector, or JinaCLIP image vector, then store the embeddings and create indexing there. Then the rest is basically database CRUD options. And if you are interested in the research side, we actually publish a lot of papers every month, and this is list here. If you're into the more in-depth or academic side of our publications, go to Jina AI News. There is the academic publications section. And that's it. Thank you.
Thank you. Thank you very much for an amazing presentation. We have questions. I'm going to start here. 2 perfect back to back.
Hi. Thanks a lot for the talk.
Thank you.
2 questions. So the first question would be, is there a particular reason that you stopped scaling both the model and the training at, I think it was 200 million parameters and 2.9 billion image text pairs seen? Because when I trained clip style models, I remember us scaling to, I think, like 20 billion image text pairs and about 2-3 billion parameters. So that was the first question. Second question, you said that you actually got better image embeddings from doing the 3-stage training, but you compared against the OpenAI clip.
So do you actually get better image embeddings if you compare to a version of your Gina model that hasn't done the long caption text embeddings or the third stage of the training?
Okay, this is a very good question. Maybe I first answer the first one. So the JinaCLIP is actually a very experimental project we have, and we don't know whether we can success. But internally, we have trained Jina embedding v2. And the Jina embedding v2 is built based on something we call JinaBird, which is English pre-training of mask language modeling of bird, but supporting very long context. And this JinaBird has around 137 million parameters. Then we basically choose something quite similar size of image tower, which to do the text image alignment. So the choice of the parameters is actually highly depends on the text tower and image tower. Text tower, we have to use JinaBird. Then image embedding, we use something they're like open source, and which is in a quite comparable size. So the final parameter size is 2.2 million, 200 million, 20, something like that. And actually, we are actually quite recently training the JinaCLIP v2, which is around 0.6 billion parameter.
That's a funny way to say 600 million.
Yeah. And the reason is we started to support more languages, such as 89 languages, and you just need more parameters to modeling more languages. And the second question, I forgot, you're asking the batch size?
No, well, you had this slide where you said, actually, with the Gina model, we get improved image embeddings.
Okay.
But it sounded like you were saying this is because of our 3-step training.
Oh.
But you compared to OpenAI CLIP and VIT B16, and so there's lots of differences between your setup and theirs. So I was wondering if you actually get better image-only embeddings because of the special care you take to get good text embeddings and of interactions those have during training.
I see. Let me answer your question. It's actually quite easy. We did the same evaluation on the same data set. We evaluated OpenAI CLIP on this data set.
Yeah, I understand your model is better than the OpenAI CLIP in getting image-only embeddings, but
yeah.
So is that all you're saying? You're not saying the 3 steps, the 3 stages of training get you there?
That's the reason we don't know why the image embedding is becoming better. Maybe it's because of the vision tower is better, because the OpenAI CLIP vision tower is basically randomly initialized. We adopted a more like modern way of training a CLIP, which is called lock image training way, which the image embedding is actually inherited from a very robust image encoder, which is called EVA02. I suspect that's the reason, but this is something I don't really care for now. Yeah.
Thank you.
Yeah, thank you.
Thank you so much for the talk and for going so deeply into the details. I also have a question about the training. I'm not sure I understood the first 2 parts of how you train it. So you have the text and image embeddings, or you generate them, and you also have this text embedding alignment. What is actually happening there, and can you maybe share some info about where you get this data and what's the rationale behind creating this alignment?
Okay, so basically in machine learning, there is a very traditional or very different, very unique way of training model is something we call twin tower network or semis network or whatever. So all we do this whenever what we observed is whenever you started to do the representation learning, you need something called contrastive learning. So what contrastive learning is, you have the representation on the left, you have the representation on the right, and you are trying to maximize the similar between these 2 representations if they are actually similar. So if they are actually, like say, an image and a caption of an image. That's why this contrastive loss works for both text and image, because in the end, JinaCLIP is trying to train a very robust, both text embedding and image embedding. So this is how contrastive learning works. And you can basically go to Google Scholar or whatever to search what is it. I think this is a very practical way to improve your model representation. So let's say you are working on the BERT model, which is a foundation model, what we call it. It doesn't work for downstream tasks. You need to fine-tune it. Let's say you want to fine-tune BERT into a text embedding model. Then you have to do this contrastive learning, giving the positive pairs or negative pairs to make the representation really works for your downstream applications, such as search. That's basically how the contrastive learning works.
Am I understanding correctly that the text pairs are not necessarily describing the same entity or in any way related?
No. Yeah, you are right. I mean, and this is something we call unsupervised training. So this is kind of supervised, but you don't really know the you don't really know the class. The only thing we need into the training data is like your search engine query and the related relevant document, or your question and the user voted document. This is a data set we built in-house from GenAI since last year. We have around 800 million text pairs for the similarity search. And this is something called unsupervised pair training. Yes.
Okay, thank you very much.
No problem.
Thank you. Okay, we'll have one here. And then while you answer the question, I'll do things on my laptop quickly.
Yeah. Thank you for the presentation.
Thank you.
I want to ask about the evaluation metric, NDCG at 10. What kind of a metric is that? How does it work? And why did you choose it?
Okay, this is basically the most widely used information retrieval metrics. G is basically gain. You can imagine it's user's information gain. And when user type a query and you find document and how much information gain you get from this document, this is something like G. And C is basically something we call cumulative. So basically you are having a ranking problem. So you have the ranking position. When the document or relevant match is at the top of the list, you have much more gain than the relevant document is at the end. So this is something called cumulative gain. Then you are also normalizing these scores, something called N. So this is something we call NDCG. And this is the most widely used metrics to evaluate search performance, I would say.
Thank you.
Thank you very much. I think that's it for the questions, right? Thank you again for the presentation.
Thank you.
It was really cool. Thank you.